All right, one of these days I'm going to stop beginning each video with, all right, but not today. So we're going to continue in Chapter 7, Section 4. Here we're going to see an example of constructing a confidence interval for, well, let's see, it's either going to be variance or standard deviation. I haven't read the problem yet, so let's take a peek now. And I'm covering up the solution because we don't want to peek and cheat. Okay, so this is example 7-14. The theme of this example is osteoporosis. Wonderful. A study of 30 women found the standard deviation of their ages was 5.2 years. Find the 95% confidence interval of the variance for the age variable. Assume the variable is normally distributed. Okay, so here they said it was a random sample, and they said that the variable is normally distributed. So those are the assumptions that we have to have in place in order to find the confidence interval for the variance or the standard deviation. Um, Most of the time, when we're doing these examples, those assumptions that we make, here, I'll just kind of show you there. These are the assumptions, right? Those assumptions, basically, they tell us that they're true. So they are fair assumptions to make. However, if we are out in the real world doing our own research and we want to, see what the best estimate, what the best range of estimate is for the standard deviation or the variance, then we have to make sure that these assumptions are actually in place. We can't just assume them to be true and have them not be true. Okay, so let's go ahead and oh, there's my other pen. Let's go ahead and do a quick write-up for, what was that? Example 7-14. So here we're continuing on in 7-4. Okay, so here the sample size n is equal to 30. The standard deviation of their ages. Okay, so it's referring to these 30 women. So that would be S, the sample standard deviation, and that was 5.2 years. Okay, all right. And we want to find the 95% confidence interval for the variance, the age variable. So we want to find 95% confidence interval for not sigma, but sigma squared. Okay, so here I'm just going to go ahead and recall that formula. So we're going to do the whole thing all at once. Because, why? Because we don't have to do it in 2 stages. Normally, well, I mean, not normally. In the past, with confidence intervals for other population parameters, we would construct a margin of error first and then do that plus or minus the center value and there construct our confidence interval. Here, it's not symmetric about the center, so we just have to remember that formula all in one shot. It's kind of nice because it's got a little pattern to it, so it depends on the sample size. It's not, well, it's not just the sample size. We can actually remember that that's our degrees of freedom. Okay, and that's in the numerator on both sides. And then the denominator, we've got a chi-squared, right? And then here's the part we never can remember well. If we want to use the book's notation and say right and left, we have to switch it up and remember that this one's going to be the right and this one's going to be the left. We switch it around. Oh, you can't see my hands across it. Well, anyhow, you have to switch it up. Or the way I like to remember this is this is the low decimal values, that's alpha over 2, And then this is going to be the higher decimal value, so that's 1 minus alpha over 2. All right, so first of all, 0.95 equals 1 minus alpha. Let's add alpha to both sides, subtract 0.95, so we get alpha is equal to 0.05. That makes sense, right? Add it up, okay. 0.05 plus 0.95, that adds up to 1. And so then what? Alpha divided by 2 is equal to 0.025, and then 1 minus alpha divided by 2 is 97.5. Right. So, the very bottom of what you can see. All right, so in order to plug into our formula here, you can see we know n, we know s, so that's the ingredients for the upstairs part of it. That's what I call the tops of fractions, or the numerators, that's upstairs. Right now, the downstairs here, we got to go to our chi-squared table and look up these values. So we got our decimal values, and then we're just going to find those decimal values in the top column. All right, well, in the top row, we're going to look up what column we're in. We're going to scan all the way down to n equals 29. All right, so I'll pause to get my distribution table, and you should maybe pause the video and try to look it up on your own. Okay, pause. Okay, so here's our distribution table, and I actually haven't done my homework yet. I haven't looked up our values yet. Sue me. No, don't sue me, just kidding. Okay, so here's a sketch of our distribution. Remember, the chi-squared distribution is skewed to the right, right? So it's big wave over here, and the tail section of it over here. All right. Now, so we've got a chi-squared value over here and a chi-squared value over here. We call these critical chi-squared values because we write them in terms of alpha. Okay, this one's alpha over 2, and this one's 1 minus alpha over 2. All right. I kind of waved my hands around and said this one, that one. So which one is which, right? Here is a handy picture in our table. Notice the table, these numbers are going to be representing the area on this side. This is area alpha. You can see that. And so the area in the right tail of the picture is the value that we're looking up. So this one right here is the alpha over 2, right? Or if you remember that you use the book's notation, right, this one would be right, okay? And this one, correspondingly, remember here, if we want this value to be alpha over 2, then the right side area here would be 1 minus alpha over 2. And that is the value that's coming out of the table, right? So imagine just shifting this over, and you would have all of that section shaded in. And then 1 minus that would be point that on that side there. Okay, so to get this value, that is 1 minus alpha divided by 2. That's that decimal that we're looking for. So then the table is actually pretty nice because, look, the large decimal values for alpha come first. So this first one, 0.975, we're going to scan all the way down to 29 for our degrees of freedom. We look up this value that says 16.047. So just write that in. 16.047, I think is what I said. Okay, so then next, we're 29 degrees of freedom all the way over to this column here. So that's corresponding to alpha equals 0.025. So that gives us 45.722. 45.722. Okay, so notice here these chi-squared values, they're all positive, remember, because 0 is the extreme left side of the distribution. There's nothing lower than 0 for a chi-squared. Kind of makes sense because what's the lowest something can be if you square it? It's going to be a positive number no matter what. Oh, 0. that would be the lowest. So also, so notice the distribution is skewed to the right. So that means our average value is going to be low, and this high value is going to be a lot higher than this low value is away from the center of the distribution. Okay. All right. So notice if you split the difference, that's not the center of this interval. That's the physical center, but that's not the proportional center of it. All right, so anyway, let's go ahead and flip the page and plug in these values into our calculation. So that's only half the battle there. We're going to complete the calculation in just a moment. Okay, and we're rolling again. I don't want to forget to press unpause and keep going ahead of you guys. All right, so here I have replaced in the formula n minus 1. I didn't plug in n. I kind of cheated and skipped that. That was what we were using for the degrees of freedom. N was 30. N minus 1 is the value that we're plugging into the formula, so that was 29. And also the degrees of freedom for our chi-squared distribution tells us which specific function in this family of functions that we're using. So the chi-squared value, notice as you shift down the various rows here, looking within the columns themselves, you notice that the chi-squared values grow as you go downward. All right, so anyway, we're plugging in 29 times 5.2 squared divided by, here notice we're dividing by the larger value. So again, this is kind of like you're remembering that the right and the left go ahead and switch up. All right, notice that the numerator is the same in both of them. It's 29 times 5.2 squared. And you're dividing by a lower value here. So when you divide by something large, the value is small, right? When you divide by something smaller, the value is larger. So this is good. This makes sense. The lower value in our interval is going to be the first value, and the higher value is going to be our end point on the right-hand side. So if you have it reversed, well, that means what? You had it reversed. Okay, so here we have 17.15. Okay, and on the other side, let's see, we'll go ahead and plug in 29 times 5.2 squared divided by 16.047, and that gives us no, hang on one second. I have to redo it. It gave me the wrong answer. Okay, so 5.2, I hit the answer function, and it was referring to the other answer. Okay, so that's better. That's 48.87. Okay, so a couple of things that I should have mentioned, but instead was grumbling at myself because my calculator betrayed me, is this. All right, not only do we have the larger value on this side and the smaller value on this side, so all is right with the world. One thing that we have to be careful about is in the formula, this is s squared. So if we are given the variance, right, that would be s squared. If we're already given s squared, we don't have to re-square it. Be careful that you don't, in fact. If we are given the standard deviation, like we were in this problem, we have to remember and square it. So that is another important thing to consider. All right. Also, consider what we are trying to find. Here it instructed us to construct the 95% confidence interval for variance. So make sure that you do that as appropriate. If it wanted the standard deviation, we would have to follow it up by then taking the square root of everything here. Okay, so let's finish there before the time runs out. down to the wire. Good day.